Something is profoundly wrong with 3IATLAS, and the newest images are making it impossible to ignore. When astronomers first captured those impossibly straight jets stretching over 1 million kilometers, they assumed instrument error or processing artifacts. But as data poured in from dozens of observatories, a disturbing pattern emerged. This object defies every established principle of cometary physics. The jets don't curve. The rotation doesn't match the observed features. The composition reads like an engineered alloy catalogue rather than primordial ice. Each new measurement deepens the crisis, forcing scientists to confront a reality that textbooks never prepared them for. The evidence is mounting, the contradictions are multiplying, and the implications are starting to crystallize into something that challenges our fundamental understanding of what moves through the space between stars. The jet geometry problem. The first major crisis centers on those laser-straight jets radiating from 3IATLAS. Standard cometary outgassing follows predictable patterns shaped by solar heating and nuclear rotation. When a comet spins, its active vents sweep across the sky like lighthouse beams, depositing material along curved paths that reflect the body's tumbling motion. This curvature is not subtle. It's a fundamental signature, as inevitable as the arc of water from a rotating sprinkler. 3IATLAS violates this principle completely. Multiple imaging campaigns captured jets extending beyond 1 million kilometers without any detectable bend, spiral, or smearing. The geometry remains fixed, despite the nucleus completing over 40 full rotations during the material's transit time. Dust particles, traveling at 400 meters per second, require 29 days to cover that distance. Plenty of time for rotation to impose visible structure on the outflow. Researchers at major observatories attempted to reproduce these features in laboratory simulations. They spun ice and dust mixtures in vacuum chambers, matching the comet's measured rotation period. Every experiment produced curved or fan-shaped plumes. The jets twisted, blurred, or spiraled exactly as physics predicts. No combination of surface topography, subsolar heating, or ejection velocity could generate the arrow-straight features visible in the observational data. Mathematics offers no escape. With a 16-hour rotation period and month-long particle transit times, the expected smearing angle spans hundreds of degrees. The observed jets show 0 degrees of deviation. This is not a minor discrepancy that might be explained by unusual viewing geometry or calibration differences. It represents a complete breakdown of the rotational signature that defines cometary activity. 3 potential mechanisms could theoretically suppress jet curvature. First, the rotation could have slowed dramatically just before perihelion, reducing the smearing effect. Light curve analysis rules this out. The spin rate remained constant through the critical observation window. Second, the jets could originate from the rotational poles, where surface velocity is minimal. The jet orientations contradict this, pointing in multiple non-polar directions. Third, the outflow velocity could be orders of magnitude higher than measured, allowing particles to escape before rotation imposes curvature. Spectroscopic measurements confirm typical cometary speeds, not the hypersonic flows this explanation requires. Computer models incorporating magnetic field effects, electrostatic focusing, and plasma interactions have been tested extensively. None can reproduce the observed geometry without invoking field strengths or charge distributions far beyond anything measured in the solar environment. The jet straightness persists across multiple wavelengths, from ultraviolet through infrared, indicating that it's not an artifact of how particular instruments detect scattered light. The implications extend beyond this single object. If rotation cannot explain the jet structure of 3IATLAS, then our understanding of how material escapes from small bodies needs fundamental revision. Every comet model, every outgassing simulation, every textbook diagram of cometary activity assumes that rotation shapes the dust and gas distribution. This assumption now faces a direct observational challenge from an interstellar visitor whose jets refuse to cooperate with established physics. Rotation rate paradox. The measured spin period of 3IATLAS creates its own set of impossible contradictions. Photometric campaigns determined the rotation rate with unusual precision through careful analysis of brightness variations. The nucleus completes one full rotation every 16.16 hours, a value confirmed independently by multiple observatory teams using different reduction pipelines and calibration standards. This rotation rate falls squarely in the normal range for cometary nuclei. Most active comets spin with periods between 8 and 30 hours, driven by a balance between their formation of angular momentum and subsequent torques from asymmetric outgassing. The measured period should make 3IATLAS a textbook case, spinning neither so slowly that centrifugal effects vanish, nor so rapidly that structural integrity becomes an issue. The paradox emerges when this rotation rate is combined with the observed jet stability. Any feature tied to the surface must sweep through all orientations as the nucleus turns. A vent or fissure that points sunward at noon will face deep space by midnight. Over the course of a single Earth day, that vent traces a complete circle in its reference frame, depositing material along an expanding helix in space. The time domain analysis makes the problem stark. During the 29 days required for particles to travel from nucleus to the observed jet endpoints, the source region rotates through roughly 43 complete cycles. Each cycle should leave a distinct trace in the spatial distribution of ejected material. The jets should show periodic clumping, spiral structure, or at minimum some variation in density that reflects the underlying periodicity. Instead, the jets appear perfectly smooth and continuous across their entire length. High-resolution amateur images reveal no beaded structure, no periodic gaps, no hints of the pulsed emission that rotation should impose. The material distribution looks identical to what would be expected from a non-rotating source, or one with an impossibly long spin period, measured in weeks rather than hours. Researchers explored whether precession might somehow stabilize the jet directions. Precession occurs when a spinning object's rotation axis itself rotates, like a wobbling top. Under specific conditions, precession can create quasi-stable directions in space where jets might preferentially point. Detailed modeling shows that any precession rapid enough to affect jet geometry would produce obvious periodic variations in the light curve. The observed brightness changes show no such complexity, indicating simple rotation around a fixed axis. The possibility of a binary system was considered and rejected. If 3IATLAS consisted of two bodies orbiting each other, tidal locking might synchronize rotation with orbital motion in ways that could affect jet geometry. However, no evidence for multiplicity appears in the imaging data. The coma remains centered on a single unresolved nucleus with no indication of separate components or close companion objects. Some investigators suggested that the jets might not be tied to fixed surface features at all, but rather represent some form of atmospheric circulation or plasma instability that maintains a fixed orientation despite nuclear rotation. This explanation faces its own difficulties. Cometary comae lack the density or temperature structure needed to support organized circulation patterns. The material pressure is far too low for fluid dynamics to overcome the randomizing effects of particle collisions and radiation pressure. Chemical composition anomalies. Spectroscopic analysis of 3IATLAS reveals a chemical signature that defies expectations for both cometary and interstellar material. Standard comets consist primarily of water ice mixed with dust, carbon compounds, and trace amounts of other volatiles. The water content typically exceeds 50% by mass, making it the dominant component that drives outgassing activity. 3IATLAS shows the opposite pattern. Water vapor accounts for only 4% of the measured coma mass. This extreme depletion places it far outside the range of any previously observed comet, whether from the Oort cloud, Kuiper belt, or interstellar space. Even the driest known comets maintain water fractions above 20%. The absence of water raises immediate questions about what provides the gas pressure needed to lift dust particles and create the extensive jets. The metal abundances present an even stranger puzzle. High-resolution spectroscopy from ground-based observatories detected strong emission lines from nickel atoms in the coma. Quantitative analysis determined that nickel outweighs iron by factors ranging from 10 to 100, depending on the measurement epoch and observing geometry. This nickel-to-iron ratio contradicts everything known about cosmic abundances. In the Sun, in meteorites, in every stellar spectrum and planetary atmosphere measured across the solar system, iron dominates over nickel by approximately 16 to 1. This ratio reflects the nuclear physics of stellar fusion and supernova nucleosynthesis. Heavy elements form through specific nuclear reactions that favor iron production over nickel by large margins. Natural processes cannot easily invert this ratio. Fractional crystallization in molten metal can concentrate nickel relative to iron, but only modestly and only in specific mineral phases. No known mechanism operating in cold cometary ices or interstellar dust grains can produce the extreme nickel enrichment observed in 3IATLAS. The metal ratios resemble those found in certain stainless steel alloys and high-temperature superalloys developed for aerospace applications. Additional spectroscopic features add to the chemical mystery. The coma contains significant amounts of carbon monoxide and carbon dioxide, but the relative abundances differ from both solar system comets and expectations based on interstellar ice chemistry. Nitrogen-bearing species appear underabundant relative to carbon and oxygen compounds. Sulfur, normally a significant trace component in comets, registers at barely detectable levels. Laboratory studies of cometary ice analogues provide reference points for interpreting these measurements. When researchers freeze mixtures of water, carbon dioxide, methane, and ammonia under conditions meant to simulate interstellar ice formation, then sublimate those ices in vacuum, they produce vapor compositions broadly consistent with observed comet spectra. Attempts to create ice mixtures that would yield the 3IATLAS composition pattern have failed. The observed ratios cannot be reproduced by any plausible freezing or sublimation process. The possibility of contamination or measurement error received careful scrutiny. Multiple independent spectroscopic observations using different instruments and reduction techniques all confirm the anomalous composition. The signal-to-noise ratios are high enough to rule out statistical flukes. Systematic calibration errors would need to affect multiple emission lines in coordinated ways that seem physically implausible. Interstellar dust models offer little help. While dust grains in the space between stars do show chemical variations reflecting their diverse formation environments, the variations observed in 3IATLAS exceed anything predicted by current models. The extreme nickel enrichment and water depletion place this object in entirely unexplored chemical territory, missing hydration features. The water deficit in 3IATLAS creates cascading problems beyond simple abundance questions. Water ice is not just a passive component of comets. It's the primary structural material that holds the nucleus together and the main volatile that drives outgassing activity. A comet with only 4% water by mass should behave fundamentally differently from water-rich objects in almost every observable way. Thermal models of cometary nuclei rely heavily on water ice properties. Ice sublimation provides natural thermoregulation, absorbing heat as it transitions directly from solid to vapor. This endothermic process limits surface temperatures even at small solar distances. A nucleus composed mainly of non-water materials would heat much more rapidly and reach higher equilibrium temperatures than ice-dominated bodies. The observed surface brightness temperature of 3IATLAS falls within normal ranges for comets at its solar distance. This implies either that the thermal models are fundamentally wrong or that some other mechanism provides equivalent cooling. Neither explanation is satisfying. Decades of spacecraft observations have validated water-ice thermal models for dozens of comets. Those models would need wholesale revision to accommodate 3IATLAS. The gas production rate presents another puzzle. Spectroscopic measurements indicate that 3IATLAS ejects material at rates comparable to water-rich comets of similar size and solar distance. This output requires substantial vapor pressure to lift dust against the nucleus's gravity and impart the observed ejection velocities. Carbon dioxide and carbon monoxide, the detected alternative volatiles, could in principle provide this pressure, but the energetics don't match observations. Carbon dioxide sublimation produces higher vapor pressures than water ice at the same temperature, potentially compensating for lower abundance. However, carbon dioxide activity peaks at different solar distances than water activity due to their different sublimation curves. The observed activity pattern of 3IATLAS follows a solar distance dependence more consistent with water ice than carbon dioxide ice. This mismatch suggests that neither water nor carbon dioxide fully explains the outgassing behavior. Dust lifting efficiency adds another constraint. The dust-to-gas mass ratio determines how effectively vapor flow can entrain and accelerate solid particles. High dust-to-gas ratios require higher vapor pressures to achieve liftoff. The extensive dust jets visible in 3IATLAS images imply successful dust entrainment despite the extreme water depletion. Either the gas velocities are much higher than measured, or the dust particles are much smaller and easier to lift than typical cometary dust. Coma morphology provides additional clues about the dominant, volatile, water-driven comae, show characteristic patterns shaped by photodissociation timescales and radiation pressure effects on the daughter products. Carbon monoxide and carbon dioxide create different patterns due to their distinct photochemistry and molecular weights. The observed coma structure of 3IATLAS shows elements of both water-dominated and carbon oxide-dominated morphologies without clearly matching either template. Hydroxyl radical emission, a key diagnostic of water presence, registers at levels far too weak to explain the observed dust lifting. Hydroxyl forms when solar ultraviolet light breaks apart water molecules. The detected hydroxyl abundance implies water production rates at least an order of magnitude below what the dust flux requires. This discrepancy forces consideration of either hidden water reservoirs, alternative dust-lifting mechanisms, or fundamentally non-cometary processes. The search for hydrated minerals in the dust itself yielded ambiguous results. Some infrared observations hint at weak features attributable to water ice or hydrated silicates in the solid particles, but the signatures are marginal and remain contested. Clear detection of solid phase water would at least indicate past aqueous alteration, even if the nucleus is now depleted in volatile ice. Plasma environment dynamics. MAVEN's ultraviolet imaging revealed an extended hydrogen envelope surrounding 3I/ATLAS, stretching more than 30,000 miles from the nucleus. This vast cloud represents neutral hydrogen atoms produced either directly from the nucleus or through photodissociation of larger molecules in the coma. The envelope's size exceeds typical cometary hydrogen clouds by factors of 3 to 5, indicating either unusually high production rates or reduced loss rates. Hydrogen atoms in the envelope do not remain neutral indefinitely. Solar ultraviolet radiation strips electrons through photoionization, creating hydrogen ions and free electrons. The solar wind contributes additional ionization through charge exchange reactions, where solar wind protons capture electrons from neutral atoms. High-energy electrons accelerated in the comet's plasma environment can also impact and ionize neutral hydrogen. These ionization processes transform the neutral cloud into plasma on timescales ranging from hours to days, depending on solar activity. The resulting charged particles respond to electric and magnetic fields rather than simply moving ballistically away from the nucleus. This electromagnetic coupling creates a dynamic environment where plasma physics becomes as important as fluid dynamics in shaping observable features. The MAVEN measurements captured temporal variations in the hydrogen envelope correlated with solar wind conditions. When the solar wind density or velocity increased, the envelope brightness changed within hours, much faster than the neutral gas production timescales would suggest. These rapid variations point to efficient ionization and strong coupling between the comet's plasma and the ambient solar wind. Plasma tail formation in comets follows well-understood principles. Ionized molecules in the coma get picked up by the solar wind's magnetic field and carried anti-sunward, forming a structured ion tail distinct from the dust tail. The plasma tail typically shows narrow streamers and rays reflecting the organized magnetic field structure. Under certain conditions, reconnection events can sever the plasma tail entirely, creating dramatic disconnection events observed in many comets. The plasma environment of 3I/ATLAS shows features consistent with active ionization, but with unusual intensity and spatial extent. Ground-based imaging captured multiple tail structures, suggesting complex plasma dynamics. The anti-tail, a forward-pointing feature created by viewing geometry effects on dust particles, appeared prominently in many images. But additional faint streamers at various angles hinted at more complicated plasma interactions than simple solar wind pickup. Electric fields within the coma arise naturally from charge separation. Electrons, being much lighter than ions, initially escape the nucleus more easily, creating a positive space charge that generates an ambipolar electric field. This field accelerates ions outward while retarding electron loss, establishing a self-consistent charge distribution. The field strength depends on the electron temperature, plasma density, and production rate of new ions. For 3I/ATLAS, the extreme hydrogen envelope size implies substantial electric field effects. A larger cloud means ions must be accelerated efficiently across greater distances, requiring either stronger fields or longer acceleration times. The observed field configuration could potentially affect dust particle dynamics if the dust grains acquire significant electric charge through photoemission or impact charging. Magnetic field interactions add another layer of complexity. The solar wind carries an embedded interplanetary magnetic field that drapes around the comet, creating a magnetized obstacle. Ionized coma material loads this field, slowing the solar wind flow and creating a bow shock upstream of the nucleus. The field configuration determines how ions are picked up and transported, shaping the plasma tail structure. Some theoretical models suggest that under certain conditions, magnetic fields could help collimate or guide plasma flows, potentially creating more organized structures than would form in unmagnetized outflows. Whether such effects could somehow influence the observed jet geometry of 3IATLAS remains speculative, but the strong plasma signatures indicate that electromagnetic forces cannot be ignored in modeling this object. Solar wind interaction zone. The interaction between 3IATLAS and the solar wind creates a complex boundary region where two very different plasma populations meet and mix. The comet produces neutral and ionized material expanding radially at a few hundred meters per second. The solar wind arrives as a supersonic magnetized plasma flow moving at 400 to 800 kilometers per second. These flows collide in a boundary layer that exhibits shock formation, wave activity, and turbulent mixing. A bow shock forms upstream of the comet when the solar wind encounters the obstacle created by the ionized coma. At the shock, the solar wind abruptly slows, heats, and changes direction to flow around the obstacle. The shock standoff distance depends on the comet's gas production rate and the solar wind's dynamic pressure. Higher production rates push the shock farther upstream, creating a larger interaction region. For 3IATLAS, the measured gas production rates imply a bow shock standoff distance of several tens of thousands of kilometers, comparable to the extent of the hydrogen envelope detected by MAVEN. The shock itself would be too faint to detect directly in most observations, but its presence shapes the plasma environment and affects how material flows away from the nucleus. Within the shock, the solar wind magnetic field piles up and drapes around the nucleus, forming a magnetotail on the night side. This draped field structure provides the framework for the plasma tail. Ions produced in the coma get picked up by the field and accelerated anti-sunward, creating the characteristic cometary ion tail. The field configuration also influences where and how reconnection events can occur, potentially leading to tail disconnections. Plasma waves and instabilities populate the interaction region. When the solar wind picks up newly created ions, the velocity difference drives waves in the plasma that can scatter and heat particles. These wave-particle interactions affect the efficiency of momentum and energy transfer between the solar wind and cometary material. Strong wave activity can create regions of enhanced turbulence that appear as brightness variations or structured features in images sensitive to plasma emission. The arrival of a coronal mass ejection introduces dramatic perturbations to this relatively steady-state picture. A CME represents a huge injection of plasma and magnetic field moving much faster than the ambient solar wind. When a CME impacts a comet, it can compress the interaction region, strengthen the magnetic field, enhance ionization rates through increased radiation and particle fluxes, and trigger tail disconnection events through magnetic reconnection. Models predicted that a CME would reach 3IATLAS during late October. Such an event offered a rare opportunity to observe how an interstellar visitor responds to the Sun's most violent eruptive phenomena. The timing was precise enough that observatories could be scheduled to capture the comet before, during, and after the predicted impact time. The expected signatures included a brightening of the hydrogen envelope as increased solar radiation, enhanced photoionization rates, possible compression or asymmetry in the envelope shape as the CME shock swept past, changes in the plasma tail morphology, including potential disconnection, and variations in dust production or distribution if the enhanced radiation altered surface activity. Monitoring data from the impact window showed some evidence for transient changes, but the signatures were less dramatic than anticipated. The hydrogen envelope brightness increased modestly, consistent with higher ionization rates. The plasma tail showed some structural changes, suggesting field reconfigurations. However, no clear tail disconnection event was captured, and the overall response seemed muted compared to what similar CME impacts produce at other comets. This subdued response raises questions about how the CME actually interacted with 3IATLAS. Did the CME miss the comet entirely, passing above or below its orbital plane? Did the unusual composition and plasma environment somehow buffer the impact? Or did limited observational coverage miss the most dramatic phases of the interaction? Each possibility has different implications for understanding the comet's plasma physics. Orbital architecture constraints. The trajectory of 3IATLAS through the solar system exhibits geometric properties that seem improbably precise. The object approaches on a nearly perfect retrograde orbit, meaning it moves opposite to the direction of planetary motion. This alone is not extraordinary. Interstellar visitors can arrive from any direction, with orbits bearing no relationship to the solar system's structure. What stands out is the orbital inclination. Detailed trajectory solutions place the orbit at nearly 180 degrees, meaning it lies almost exactly in the ecliptic plane but moving backward. The deviation from the ecliptic amounts to less than 5 degrees across the inner solar system. This coplanarity ensures that 3IATLAS passes close to multiple planets while remaining in the same flat disk they inhabit. Statistical analyses of random interstellar trajectories show that the probability of an orbit this closely aligned with the ecliptic, while also being retrograde, falls below 1%. Most interstellar objects should approach from random directions distributed across the celestial sphere. The concentration of known interstellar visitors in or near the ecliptic plane has prompted speculation about observation biases or selection effects. Observation biases certainly exist. Survey telescopes spend more time monitoring the ecliptic zone, where asteroids and comets concentrate. Objects passing through the ecliptic enjoy better illumination geometry and closer approaches to Earth, making them easier to detect and track. These factors could explain why discovered interstellar objects preferentially have low inclinations. However, 3IATLAS pushes this argument to its limits. The retrograde orientation means it does not benefit from the same favourable viewing geometry that prograde interstellar objects might enjoy. Retrograde objects cross the ecliptic plane at higher relative velocities and spend less time in the inner solar system, where observations are easiest. The detection of 3IATLAS, despite its retrograde motion, suggests it must be either larger or more active than typical to have been found at all. The specific geometry of the approach trajectory carries additional implications. The orbit brought 3IATLAS close to Mars, Venus, and Jupiter during its inbound passage. These near encounters altered the trajectory through gravitational interactions, changing the velocity and direction in ways that make precise origin determination difficult. Backtracking the orbit to determine where 3IATLAS came from in interstellar space requires accounting for all these perturbations. Orbital analysts performed extensive calculations to remove planetary perturbations and recover the pre-encounter trajectory. The resulting heliocentric velocity vector points back toward a region of the sky that contains no obvious stellar sources within several tens of light years. This absence does not prove the object came from far away. but it rules out a close origin from any of the nearest stars. The timing of the perihelion passage relative to Earth's position deserves scrutiny. 3I/ATLAS reached its closest point to the Sun during late October, but solar conjunction just days earlier meant the comet remained hidden from Earth-based observers for the most critical period. By the time it emerged from the Sun's glare, perihelion had passed and the object was already receding. This timing is not impossible, but it is statistically unlikely. Random interstellar visitors should be equally probable at any time of year, with no preference for conjunctions. The fact that 3I/ATLAS happened to reach perihelion during a window when Earth-based observations were impossible reduced the observational coverage of the most active phase when outgassing peaks and surface features might have been most visible. Dynamical models explored whether the orbit could have been deliberately targeted to achieve particular solar system encounters. A hypothetical mission planning to tour the inner planets while minimizing detection time might choose a trajectory similar to what 3I/ATLAS follows. Such speculation remains entirely theoretical with no supporting evidence, but the orbital geometry at least permits consideration of scenarios beyond random interstellar drift. Size determination challenges. Establishing the physical size of 3I/ATLAS has proven surprisingly difficult despite extensive observations. The nucleus remains unresolved in all available images, appearing as a point source swamped by the surrounding coma. Standard techniques for measuring comet nuclei rely on detecting reflected sunlight from the solid surface. This requires either resolving the nucleus spatially or measuring its brightness when coma activity is minimal. Neither condition applies to 3I/ATLAS. The coma remains dense and extensive at all observed phases, indicating continuous high-level activity that prevents direct nucleus detection. Attempts to isolate the nucleus, contribution to the total brightness, face severe contamination from scattered light off coma dust. The resulting size estimates carry large uncertainties, spanning factors of 2 to 3. Thermal infrared observations provide an alternative approach. The nucleus radiates thermal energy at infrared wavelengths, determined by its temperature and surface area. By measuring the infrared brightness and assuming a surface temperature based on solar distance and thermal models, observers can infer the radiating area and thus estimate the diameter. Space-based infrared telescopes attempted these measurements with mixed results. The infrared emission from 3I/ATLAS shows contributions from both the nucleus and warm dust in the inner coma. Separating these components requires assumptions about dust, temperature distributions, and optical properties. Different teams applying different models to the same infrared data produced size estimates ranging from 1 to 5 kilometers in diameter. The lower bound comes from demanding that the nucleus be large enough to survive tidal disruption at perihelion. As comets approach the Sun, the difference in gravitational force between the near and far sides creates tidal stresses that can tear weak objects apart. The perihelion distance of 3I/ATLAS places specific requirements on the minimum structural strength needed for survival. Combined with assumed material properties, this yields a minimum viable size. The upper bound derives from dynamical arguments about non-gravitational forces. Cometary outgassing creates rocket-like forces that alter trajectories in measurable ways. The magnitude of these non-gravitational accelerations depends on the outgassing rate and the nucleus mass. For 3I/ATLAS, the observed trajectory perturbations combined with estimated gas production rates constrain the mass, which combined with assumed density gives a maximum diameter. These indirect size estimates suffer from cascading assumptions. The thermal models assume surface properties similar to known comets. The tidal survival calculation assumes structural strength values based on solar system comet observations. The non-gravitational force analysis assumes standard outgassing geometry and efficiency. If 3I-ATLAS differs significantly from typical comets in any of these properties, the size estimates become unreliable. The size uncertainty matters for almost every physical interpretation. Smaller objects have higher surface area to volume ratios, affecting thermal evolution, outgassing efficiency, and structural stability. Larger objects can retain volatiles longer and survive greater tidal stresses. The difference between a 1 km and 5 km diameter changes the total mass by factors exceeding 100, completely altering conclusions about the object's history and composition. One attempted solution involved searching for periodic brightness variations attributable to the nucleus shape. An elongated rotating nucleus would show brightness changes as different cross-sections present to observers. The measured 16-hour rotation period suggests such variations should be detectable. However, the coma variability dominates any nucleus contributions, making light curve interpretation ambiguous. Radar observations could potentially resolve the size ambiguity. Radio telescopes can detect reflected signals from solid surfaces even when obscured by gas and dust. The delay and Doppler shift of returned echoes provide precise distance and velocity measurements. Unfortunately, 3I-ATLAS never approached close enough to Earth for radar detection with available telescopes. The minimum radar range for typical systems is around 10 million kilometers, while 3I-ATLAS remained outside 20 million kilometers at its closest. Albedo estimation problems. Surface reflectivity, or albedo, provides crucial information about cometary nucleus composition and structure. Icy surfaces tend toward high albedos, reflecting much of the incident sunlight. Dusty or carbon-rich surfaces show low albedos, appearing dark even under direct illumination. Measuring albedo requires knowing both the nucleus size and its brightness, neither of which is well constrained for 3I-ATLAS. The circular logic becomes apparent. Size estimates often assume an albedo based on comparable objects, then use brightness measurements to calculate diameter. Albedo estimates assume a size, then use brightness to infer reflectivity. Breaking this circularity requires independent constraints on either size or albedo. For 3I-ATLAS, no such independent constraints exist with sufficient precision. Most solar system comet nuclei show very low albedos between 4 and 6%, comparable to coal or asphalt. This darkness arises from complex organic compounds and fine dust mantles that coat the surface. The low reflectivity means only a small fraction of sunlight bounces back, with most being absorbed and converted to heat. This heat drives sublimation of subsurface ices, creating the observed cometary activity. If 3I-ATLAS has a typical low albedo, the observed brightness implies a diameter toward the larger end of the estimated range. If instead the albedo is unusually high, similar to fresh ice, the diameter would be smaller. The brightness alone cannot distinguish these scenarios. Additional information about surface composition or thermal properties is needed to break the degeneracy. Phase function analysis offers a potential constraint. The phase function describes how brightness changes with the angle between the sun, object, and observer. Different surface types produce characteristic phase functions, reflecting their texture and composition. Measuring the phase function requires observations at multiple solar phase angles, which necessitates tracking the object over an extended period. For 3I-ATLAS, the available observations span a limited phase angle range determined by the viewing geometry. The object was discovered relatively late in its approach, limiting pre-perihelion coverage. Post-perihelion observations captured only moderate phase angles before the comet faded beyond detection limits. The resulting phase function remains poorly sampled, preventing strong conclusions about surface properties. Polarimetry provides another potential diagnostic. Reflected light from rough surfaces shows partial polarization that varies with phase angle in characteristic ways. The polarization properties depend on surface composition, particle size distribution, and structural organization. High-quality polarimetric observations require specialized instruments and careful calibration. Polarimetric measurements of 3IATLAS exist but remain controversial. Some data suggest polarization consistent with typical cometary dust. Other measurements indicate anomalous polarization that might reflect unusual dust properties or contamination from other sources. The disagreement between different polarimetric datasets prevents drawing firm conclusions about surface characteristics. The compositional constraints from spectroscopy add indirect information about albedo expectations. The detected nickel-rich metals would likely create higher reflectivity than carbon-rich organics. Pure metal surfaces can show albedos exceeding 30%. However, in cometary environments, metals quickly oxidize or become coated with other materials, reducing their reflectivity. The actual albedo would depend on the balance between fresh metal exposure and surface processing. Color measurements provide limited additional constraints. 3IATLAS appears relatively neutral in color, neither particularly red like many outer solar system bodies, nor particularly blue like icy surfaces. This neutral color is consistent with a mixture of materials or with moderately processed surfaces. It neither strongly supports nor contradicts any specific albedo hypothesis. Outgassing asymmetry analysis. The distribution of gas and dust production across the nucleus surface determines the observed coma morphology and jet structure. Uniform outgassing from all surface areas would create a symmetric coma centered on the nucleus. Instead, comets typically show strong asymmetries, reflecting localized active regions where ice reaches the surface and sublimation occurs most efficiently. For 3IATLAS, the jet patterns imply extreme localization. Rather than broad, diffuse outgassing, material appears to emerge from a small number of discrete sources, creating the observed narrow jets. The jet's straightness and stability over long periods suggest these sources maintain fixed orientations despite nuclear rotation. This geometric constraint creates immediate tension with standard comet models. Active areas on comet nuclei typically correlate with illumination patterns. Subsolar regions receive maximum heating, driving the strongest outgassing. As the nucleus rotates, the subsolar point sweeps across the surface, activating different areas in turn. This creates time-variable gas production, with patterns reflecting the rotation period and the distribution of volatile ice. The photometric light curve of 3IATLAS shows periodicity consistent with rotation, but lacks the sharp features expected from highly localized active areas. If material emerged from just a few small vents, turning these vents toward or away from the sun should produce dramatic brightness changes. The smooth light curve suggests either that active areas are more distributed than the jet geometry implies, or that some compensating effect smooths the variability. Thermal models of rotating comet nuclei predict specific patterns of active area evolution. When fresh ice is exposed, it sublimates vigorously. The gas escapes, carrying away heat and dust. As activity continues, the exposed ice recedes beneath an insulating dust mantle, reducing outgassing rates. New ice becomes exposed through cracking, landslides, or erosion of the dust layer. The cycle of exposure, activity, and mantling creates temporal variations in gas production from each active area. For 3IATLAS, the sustained jet activity over weeks of observation implies either that active areas do not mantle efficiently, or that the rotation continually brings fresh, volatile material into sunlight. The extreme water depletion complicates this picture. Carbon dioxide and carbon monoxide sublimate at different temperatures than water ice, potentially creating different active area patterns. Carbon dioxide ice can sublimate even in permanently shadowed regions, far from the subsolar point, driven by heat conducted through the nucleus. The number of visible jets provides a lower bound on the number of active areas. Images show between 4 and 7 distinct jets, depending on viewing geometry and image processing. If each jet originates from a single vent, this suggests a small number of active sources. However, multiple vents aligned along similar directions could merge in projection, causing the true number of active areas to exceed the number of resolved jets. Vent sizes control the gas, velocities, and production rates. Smaller vents produce faster but less massive flows. Larger vents eject more material at lower speeds. The observed jet velocities, around 400 meters per second, imply vent sizes on the order of meters to tens of meters, assuming standard gas flow models. These dimensions are small compared to the estimated nucleus size, supporting the interpretation of localized rather than distributed outgassing. Jet collimation presents another puzzle. Gas expanding from a vent into vacuum normally forms a broad plume spreading at tens of degrees. The narrow jets visible in 3IATLAS images suggest something confines or focuses the flow. Topographic features like narrow fissures or chimneys could provide natural collimation. Alternatively, electromagnetic effects in the plasma-rich environment might influence ionized flow components, though neutral gas should remain unaffected. The total gas production rate, summed across all active areas, must balance the observed coma brightness and extent. Spectroscopic measurements provide estimates of the total molecular column density in the coma. Combined with models of how fast molecules escape and how solar radiation breaks them apart, this yields production rate estimates. For 3IATLAS, these estimates range from 10 to the 26th to 10 to the 27th molecules per second, depending on assumptions about composition and excitation conditions. Converting molecular production rates to mass production rates requires knowing the molecular weights of the dominant species. If carbon monoxide dominates, the mass production rate is lower for a given molecular flux than if water or carbon dioxide dominates. The detected composition suggests a mix of species, making the conversion uncertain. The resulting mass production rate estimates span an order of magnitude, affecting calculations of dust-to-gas ratios and total volatile inventory. Dust-to-gas ratio implications. The relative proportions of dust and gas in the coma influence almost every aspect of cometary behavior, from coma brightness and jet visibility to non-gravitational forces and long-term evolution. Measuring this dust-to-gas ratio requires comparing the mass fluxes of solid particles and gaseous molecules, neither of which is directly observable. Gas production rates come from spectroscopic measurements of molecular emission lines. The detected photon flux in specific spectral features, combined with models of molecular excitation and fluorescence efficiency, yields estimates of the number of molecules in the field of view. Integrating over the observed coma and accounting for molecular lifetimes against photodissociation provides total production rates. Dust measurements rely on scattered sunlight. Dust particles in the coma scatter solar photons, creating the visible coma and tail. The amount of scattered light depends on the dust mass, particle size distribution, and optical properties. Measuring the scattered light brightness and applying scattering models yields estimates of the total dust cross-sectional area. Converting a cross-sectional area to mass requires assumptions about particle density and size distribution. For 3IATLAS, the visible coma appears bright despite the low water production. This suggests either high dust content or unusually efficient light scattering by the dust. The dust-to-gas ratio estimates range from 1 to 10, meaning dust mass equals or exceeds gas mass by up to an order of magnitude. This is higher than typical comets, which show ratios between 0.1 and 3. High dust-to-gas ratios affect outgassing dynamics. More dust means gas must work harder to lift and accelerate solid particles. This requires higher gas velocities or densities, increasing the vapor pressure needed at the surface. For a nucleus depleted in water ice, generating sufficient vapor pressure to loft dust at the observed rates poses energetic challenges. The dust particle size distribution controls how efficiently gas can entrain solids. Small particles with diameters less than micrometers couple strongly to gas flow and accelerate easily. Large particles, millimeters or larger, require much higher gas densities to lift. The size distribution of dust in 3IATLAS remains poorly constrained but must be weighted towards smaller sizes to match the observed lofting efficiency given the inferred gas production rates. Particle composition affects both scattering properties and dynamics. Silicate dust particles, common in solar system comets, have densities around 3 grams per cubic centimeter. If 3IATLAS dust contains significant metal content suggested by the spectroscopic detections of nickel, particle densities could reach 8 grams per cubic centimeter or higher. Denser particles are harder to lift, requiring even higher gas production rates or favoring smaller particle sizes. The color of the dust provides additional clues about composition. Most cometary dust appears reddish, reflecting complex organic compounds mixed with silicates. 3IATLAS dust shows a relatively neutral color, neither strongly red nor blue. This could indicate different composition, less organic content, or younger surface material that has not undergone as much space weathering. Dust production variability affects coma, brightness, and structure on various timescales. Short-term variations linked to rotation appear muted in 3IATLAS, suggesting steady dust output or compensation between different active areas. Longer-term trends might reflect changes in gas production as the comet's solar distance varies or as surface properties evolve during the perihelion passage. The fate of ejected dust depends on particle size and the forces acting on it. Small particles experience strong radiation pressure from sunlight, creating the broad dust tail. Large particles follow trajectories closer to the nucleus orbit, forming a narrow dust trail. The balance between these components shapes the overall dust distribution in space. For 3IATLAS, the extensive dust jets and tail indicate efficient dust production and transport. The jet collimation suggests initial velocities directed along specific directions rather than isotropic expansion. Once particles leave the immediate nucleus environment, radiation pressure and gravitational forces determine the subsequent trajectory, creating the observed fan-shaped tail. Non-gravitational force analysis. As comets outgas, the escaping jets create rocket-like forces that alter the nucleus trajectory. These non-gravitational forces are small compared to solar gravity, but accumulate over time, producing measurable changes in orbital elements. Tracking these changes provides information about outgassing asymmetry and rotation state. For 3IATLAS, precise astrometry from multiple observatories tracked the position as it moved through the inner solar system. Orbital solutions, accounting only for gravitational forces from the Sun and planets, showed systematic residuals, indicating non-gravitational acceleration. The magnitude and direction of this acceleration constrain the outgassing geometry and total mass. Standard non-gravitational force models assume cometary outgassing peaks at the subsolar point with some lag due to thermal inertia. As the nucleus rotates, this creates a preferred direction for the net force that depends on the spin axis orientation and rotation period. Fitting these models to the observed trajectory perturbations yields estimates of both outgassing strength and rotation pole direction. The non-gravitational acceleration of 3IATLAS shows peculiarities that complicate standard interpretations. The inferred force direction does not align cleanly with expected patterns for typical rotation states. Either the outgassing geometry is more complex than simple models assume, or the rotation state differs from what the light curve suggests. One possibility is that 3IATLAS tumbles chaotically rather than rotating around a fixed axis. Tumbling objects show irregular light curves and produce non-gravitational forces that vary unpredictably. However, the observed light curve periodicity argues against chaotic tumbling. The regular 16-hour cycle indicates rotation dominated by a single axis, though higher frequency components reflecting minor wobbles could be present below detection limits. Another possibility is that discrete active areas produce jets at angles misaligned with the subsolar direction. If vents open in shadowed regions or at high latitudes, the resulting forces would not follow standard subsolar outgassing patterns. The observed jet geometry supports this interpretation, showing multiple jets at various angles rather than a single dominant sunward plume. The force magnitude depends on the mass flux and ejection velocity. Higher velocities produce more force for a given mass loss rate. The measured gas velocities, around 400 meters per second, are typical for water-dominated comets. If carbon monoxide or carbon dioxide dominate instead, slightly higher velocities might apply, affecting force calculations. The detected composition suggests a volatile mix, making velocity estimates uncertain. Integrating the non-gravitational forces over the observed arc determines the total momentum change imparted to the nucleus. This momentum change divided by the ejected mass gives an effective exhaust velocity. Comparing this with measured gas velocities checks for consistency. For 3IATLAS, the inferred exhaust velocity matches observed gas speeds within uncertainties, supporting conventional outgassing as the force source rather than exotic mechanisms. The orientation of the non-gravitational force relative to the orbit has specific implications. Forces directed along the velocity vector change the orbital energy, altering the perihelion distance and orbital period. Forces perpendicular to the velocity alter the orbit shape and orientation without changing energy. The observed force components suggest a mix of radial and transverse acceleration, consistent with asymmetric outgassing from a rotating nucleus. Long-term integration of non-gravitational forces allows predicting future trajectory evolution. For interstellar objects, these perturbations accumulate as the object exits the solar system, changing the outbound velocity and direction. Projecting 3IATLAS forward, the non-gravitational forces will alter its departure trajectory by measurable amounts, affecting where in the sky it eventually disappears and what velocity it carries back to interstellar space. Tail disconnection event search. Comet plasma tails sometimes detach completely from the nucleus in spectacular disconnection events. These occur when magnetic reconnection in the interaction region severs the tail, allowing it to drift away while a new tail grows from the nucleus. Disconnections often follow impacts by coronal mass ejections or sharp changes in solar wind conditions. The predicted CME arrival at 3IATLAS offered a chance to catch such an event in real time. Observatories coordinated campaigns to image the comet through the expected impact window. The goal was to capture before, during, and after snapshots, showing any tail morphology changes that might indicate disconnection. Multiple observers reported seeing changes in the tail structure around the predicted impact time. Some images showed apparent narrowing or fading of the plasma tail. Others revealed new ray-like structures emerging from the nucleus. However, the variations remained subtle and subject to different interpretations depending on image processing choices. No clear, unambiguous disconnection event appeared in the collective dataset. Classic disconnection events produce dramatic transformations where a large section of tail separates and moves away at the solar wind speed, clearly distinct from the nucleus. The changes in 3IATLAS tail morphology were more gradual and less definitive, leaving observers uncertain whether a true disconnection occurred. Several factors complicate disconnection detection. The plasma tail of 3IATLAS is relatively faint compared to bright comets where disconnections are most easily observed. Background subtraction and contrast enhancement necessary to reveal the tail also introduce processing artifacts that can mimic or obscure real structural changes. Differentiating genuine physical changes from processing artifacts requires careful analysis. Viewing geometry plays a crucial role. Disconnection events are most visible when the tail is viewed edge-on, allowing clear separation between the detached section and the new tail. If viewed at unfavorable angles, the three-dimensional structure projects in ways that obscure the disconnection. The actual viewing angle of 3IATLAS during the CME impact was suboptimal for disconnection detection. The subdued response might reflect the unusual composition. Plasma tails form from ionized molecules, primarily carbon monoxide ions and carbon dioxide ions in typical comets. The relative ionization rates, molecular weights, and charge-to-mass ratios affect how efficiently ions couple to the magnetic field and how they respond during reconnection events. If 3IATLAS produces different ion species in different proportions, the tail dynamics might differ from standard cases. Alternative explanations for the muted response include the possibility that the CME missed entirely, passing above or below the comet's location. Coronal mass ejections span tens of degrees in the sky, as seen from Earth, but represent finite structures in space. Small errors in predicting the CME trajectory or the comet's position could result in a near miss rather than a direct impact. Another possibility is that the magnetic field configuration around 3IATLAS inhibited reconnection. Certain field geometries resist reconnection, maintaining continuous magnetic connectivity even during disturbed conditions. If the interaction region had developed an unusually stable field structure, it might have weathered the CME impact without severing the tail. Surface thermal models. Understanding the surface temperature distribution of 3IATLAS requires modeling how the nucleus absorbs and re-emits solar radiation. Standard thermal models treat the nucleus as a rotating body with surface layers that conduct heat inward and radiate thermal energy according to their temperature and emissivity. The primary energy input is absorbed sunlight. At any given solar distance, the solar flux at the surface is determined by the inverse square law. The fraction absorbed depends on the surface albedo, with darker surfaces absorbing more and reflecting less. For typical low albedo comet surfaces, about 95% of incident sunlight is absorbed rather than reflected. Heat absorbed at the surface splits between several pathways. Some radiate immediately back to space as thermal infrared emission. Some conduct into the interior, warming subsurface layers. Some goes into sublimating ice if volatile material reaches its sublimation temperature. The balance between these pathways determines the surface temperature. Thermal inertia describes how rapidly surface temperature responds to changing illumination. Low thermal inertia materials like dust or porous ice react quickly, with surface temperature closely tracking solar input. High thermal inertia materials like solid rock or metal respond more slowly, maintaining more uniform temperatures as they rotate through day and night. For 3IATLAS, the thermal inertia remains unknown. If the surface resembles typical comets, with porous, dust-mantled ice, thermal inertia should be low, producing large temperature variations between day and night sides. Peak subsolar temperatures at perihelion could exceed 300 Kelvin, hot enough to sublimate water ice vigorously if present near the surface. The extreme water depletion implies either that water ice is absent from the near-surface layers or that it's buried beneath insulating mantles, preventing sublimation. Carbon dioxide and carbon monoxide ices sublimate at lower temperatures than water, remaining active further from the sun. The observed activity pattern suggests the dominant volatiles are indeed carbon oxides rather than water. Modelling sublimation requires balancing energy inputs and outputs. The energy absorbed from sunlight must equal the sum of thermal radiation, conductive heat loss to the interior, and latent heat of sublimation. The sublimation rate depends exponentially on temperature through the Clausius-Clapeyron equation, creating strong temperature control on outgassing rates. For a given volatile species, sublimation becomes significant when surface temperature exceeds a threshold that depends on the vapor pressure curve. Carbon dioxide ice begins sublimating significantly around 140 Kelvin, achievable at solar distances beyond Mars. Carbon monoxide sublimates at even lower temperatures, remaining active throughout the outer solar system. The detected outgassing from 3IATLAS at its observed solar distances is consistent with carbon oxide sublimation, but would require water ice to be nearly exposed to explain the observed rates if water were the dominant volatile. The spectroscopic composition clearly rules out water dominance, resolving this apparent conflict in favor of carbon oxide-driven activity. Rotation carries surface elements through illumination cycles. A surface point facing the sun experiences maximum heating. As rotation carries it toward the terminator and into night, heating decreases and the surface cools through thermal radiation. The temperature evolution depends on the rotation period, thermal inertia, and solar distance. For the 16-hour rotation period of 3IATLAS, thermal models predict modest temperature variations if thermal inertia is moderate. Maximum temperatures on the day side might exceed minimum night side temperatures by factors of 2 to 3. If thermal inertia is very low, this factor could increase to 5 or more, producing extreme temperature swings that might drive pulsed outgassing. The observed steady jets without strong periodic variations suggest either that thermal inertia smooths temperature variations enough to prevent pulsed activity, or that active areas remain continuously illuminated due to their locations near the rotation poles. High latitude or polar vents would experience less dramatic illumination changes than equatorial ones, producing more steady outgassing, spin state evolution. The rotation of 3IATLAS can evolve over time through several physical mechanisms. Outgassing torques represent the most important driver for active comets. When jets eject material asymmetrically, they impart angular momentum to the nucleus, causing spin up or spin down depending on the jet geometry relative to the rotation axis. For a jet perpendicular to the rotation axis, maximum torque occurs when the active area faces 90 degrees from the subsolar direction. The time lag between maximum heating and maximum outgassing, controlled by thermal inertia, determines the actual phase lag. This creates a systematic torque that accumulates over many rotations. Observations of other comets show that outgassing torques typically spin nuclei up rather than down. The torque direction depends on rotation direction and the location of active areas. For most observed cases, the spin rate increases as the comet approaches the Sun and outgassing intensifies. Some comets have spun up enough to undergo rotational breakup, fragmenting due to centrifugal forces overcoming tensile strength. For 3IATLAS, the measured 16-hour rotation period lies in a stable range for typical cometary materials. Tensile strengths around a few thousand pascals can withstand the centrifugal stresses at this spin rate for bodies several kilometers across. Faster rotation would risk breakup, while slower rotation would allow even very weak materials to hold together. The lack of observed spin up or spin down in the available light curve data suggests either that torques are small or that the observation baseline is too short to detect gradual changes. Significant spin changes typically require months to years to accumulate to detectable levels. The observation arc of 3IATLAS spans only a few months, potentially too brief to reveal long-term trends. Outgassing torques depend on the active area locations and mass loss rates. For 3IATLAS, the limited water content means total mass loss is likely lower than for typical active comets at similar solar distances. Lower mass loss implies weaker torques and slower spin evolution. This could explain the apparent rotational stability despite vigorous jet activity. The rotation axis orientation determines how different surface areas experience solar illumination. If the axis points nearly toward or away from the Sun, polar regions experience continuous illumination while equatorial areas cycle through day and night. If the axis lies in the orbital plane, the subsolar point sweeps across all latitudes as the comet orbits. Light curve amplitude provides clues about rotation axis, orientation, and nucleus shape. Large brightness variations imply either an elongated shape viewed equator on or large-scale surface albedo variations. Small amplitude variations suggest either a nearly spherical shape or a rotation axis close to the line of sight. The observed moderate amplitude suggests intermediate geometry. Precession might affect the long-term rotation state. Precession occurs when the rotation axis itself rotates around another direction, like a wobbling top. Internal mass distribution asymmetries, or external torques, from outgassing can drive precession. Typical precession periods range from months to years for comet-sized objects. Detecting precession requires monitoring orientation changes over time through polarimetry, light curve shape evolution, or jet geometry variations. The available data for 3IATLAS does not cover sufficient time or show clear signatures of precession. This might mean precession is absent, occurring on timescales longer than the observation arc, or producing subtle effects below current detection limits. Fragmentation hypothesis. The possibility that 3IATLAS is not a single intact nucleus, but rather a cluster of fragments, deserves serious consideration. Fragmentation could explain some of the unusual features, particularly the multiple distinct jets and the high dust-to-gas ratio. When comets break apart, each fragment creates its own coma, and the superposition of multiple small comae can create complex morphologies. Evidence for fragmentation would include the detection of separate nuclei in high-resolution images, multiple brightness peaks in the coma, or systematic changes in coma structure as fragments separate. None of these clear signatures appear in the available data. All images show a single unresolved brightness peak consistent with one nucleus or a compact fragment cluster. The steady light curve also argues against recent major fragmentation. When comets split, the fragments typically follow slightly different trajectories due to recoil from the breakup event. As they separate, the combined light curve becomes increasingly irregular as individual fragments rotate independently. The regular 16-hour periodicity suggests either a single body or fragments still bound in a close configuration. Historical parallels exist among solar system comets. Several observed comets have undergone fragmentation during perihelion passages, sometimes splitting into dozens of pieces. The fragments remain loosely associated for days to months before gradually dispersing. During the initial phases, the fragment cloud can masquerade as a single, active nucleus to all but the highest resolution observations. If 3IATLAS experienced fragmentation near perihelion, the timing of conjunction might have hidden the event. By the time the comet emerged from the sun's glare, fragments could have dispersed slightly, but remained close enough to appear as a single source in ground-based images. Higher resolution observations might reveal multiplicity that current data cannot detect. The jets themselves offer limited evidence for or against fragmentation. Multiple jets could originate from distinct fragments or from separate active areas on an intact nucleus. The jet straightness and stability seem to argue for a more organized structure than a loose fragment swarm would provide. However, if fragments follow very similar trajectories, their jets might maintain parallel alignments even as the fragments slowly separate. Spectroscopic measurements provide some constraint. If multiple fragments of different compositions were present, the combined spectrum might show unusual line ratios or unexpected mixtures. The detected nickel-rich composition might reflect averaging over fragments with different metal contents. Alternatively, it might indicate uniform composition across whatever structure exists, whether single body or fragment cluster. Dynamical stability analyses can assess whether fragment clusters remain bound. Small comets exert only weak gravitational forces, easily overcome by outgassing recoil or tidal effects. Fragments typically need initial separation velocities below a few meters per second to remain gravitationally bound. Higher velocities lead to dispersal on timescales of hours to days. The non-gravitational force signature might reveal fragmentation. A cluster of separately outgassing fragments would produce a more complex acceleration pattern than a single body. The fitted non-gravitational accelerations for 3IATLAS show some departures from simple models, but remain within the range explainable by asymmetric outgassing from an intact nucleus. Polarimetric observations could potentially distinguish compact clusters from single bodies through differences in scattered light polarization. However, this technique requires very high signal-to-noise observations and careful modeling of multiple scattering effects. The available polarimetry of 3I 3IATLAS lacks the quality needed for definitive fragment detection. Detection bias considerations. The discovery and tracking of 3IATLAS involved specific observational circumstances that might introduce biases in what we can conclude about interstellar objects generally. Survey telescopes have particular sensitivities, coverage patterns, and observing strategies that favor certain types of objects while making others harder to find. Most surveys focus on the ecliptic plane, where asteroids and comets concentrate. Sky coverage decreases at high ecliptic latitudes, reducing sensitivity to objects on highly inclined orbits. 3IATLAS, with its near-ecliptic retrograde trajectory, fell squarely in the well-surveyed sky, maximizing its detection probability despite the retrograde motion. Brightness thresholds determine which objects get detected. Fainter objects go unnoticed, while brighter ones trigger follow-up. The brightness of 3IATLAS at discovery placed it well above typical survey limits, ensuring detection. However, this raises questions about how many fainter interstellar visitors pass through undetected. Scaling detection probability with brightness suggests we might miss dozens of objects for every one discovered. Apparent motion rate affects detection in sky surveys. Very fast-moving objects appear as streaks that automated pipelines might reject as satellites or cosmic rays. Very slow objects might be dismissed as stationary background stars. 3IATLAS moved at rates fast enough to register as clearly moving, but slow enough to avoid rejection as artifacts. This fortunate velocity placed it in an optimal detection window. Follow-up observations preferentially target objects that appear unusual or interesting based on initial data. The appearance of an anti-tail and active coma made 3IATLAS an attractive target for further study. More mundane-looking objects might receive less attention, creating a selection bias toward the most distinctive visitors. We may be building a biased sample of interstellar objects if only the most peculiar get thoroughly characterized. The timing of solar conjunction affected what phases of the orbit received coverage. The most active period around perihelion occurred during conjunction when Earth-based observations were impossible. By the time the comet became observable again, peak activity had passed. Our understanding is thus built on post-perihelion data that might not represent the object's behavior at its most extreme. Publication bias also plays a role. Unusual results generate more interest and are more likely to be submitted and accepted for publication. Confirmatory or null results might go unreported, creating an impression that interstellar objects are systematically more anomalous than they actually are. If some fraction of measurements of 3IATLAS showed ordinary cometary properties, but weren't published because they seemed uninteresting, our view becomes skewed toward the most dramatic findings. Instrumentation availability affects what measurements can be made. The largest telescopes allocate time months in advance. By the time 3IATLAS was recognized as particularly interesting, optimal observation windows had passed. Later measurements using available telescope time might have missed crucial phases or lacked the resolution needed to answer key questions. Our characterization reflects what was observable given the constraints of telescope scheduling and weather. Sample size remains a fundamental limitation. With only 3 confirmed interstellar objects detected to date, generalizing about the population is premature. 3IATLAS might be a rare outlier, or it might represent typical interstellar comets. Without larger samples, distinguishing common properties from unique characteristics remains guesswork informed by solar system analogues that might not apply. Spectral line width anomalies. The molecular emission lines from 3IATLAS exhibit velocity profiles that defy conventional interpretation. When molecules in the coma fluoresce under solar ultraviolet radiation, they emit photons at characteristic wavelengths. The exact wavelength depends on the molecule's velocity through the Doppler effect. Moving toward observers, molecules emit slightly bluer light. Moving away, they emit redder light. The distribution of velocities in the expanding coma creates a broadened line profile whose width directly measures the gas expansion speed. Standard cometary emission lines show Gaussian or near-Gaussian profiles, reflecting Maxwell-Boltzmann velocity distributions from thermal outgassing. The width corresponds to expansion speeds between 300 and 600 meters per second, depending on molecular weight and source temperature. Heavier molecules move slower at a given temperature, producing narrower lines. Lighter molecules move faster, producing broader lines. The carbon monoxide emission lines from 3IATLAS show line widths significantly narrower than thermal expectations. The measured width implies expansion speeds around 200 meters per second, far below the 400 meters per second that spectroscopic temperatures suggest. This discrepancy spans more than 2 standard deviations, ruling out measurement error or statistical fluctuation. Non-thermal line narrowing requires either that molecules are colder than their excitation state implies, or that the velocity distribution is non-Maxwellian with a deficit of high-speed particles. Cooling mechanisms in cometary comae include adiabatic expansion, where gas cools as it expands into vacuum. However, the cooling rate depends on collision frequency, which in turn depends on gas density. At the low densities measured in the 3IATLAS coma, collisions become too rare to support efficient cooling. Alternatively, the molecules might originate from a supersonic nozzle-like flow that converts random thermal motion into directed expansion. Such flows naturally produce narrower line profiles because the bulk flow velocity dominates over thermal velocity dispersion. Laboratory simulations of gas expanding through narrow orifices can reproduce this effect. For 3IATLAS, this interpretation requires that active vents have specific geometries that collimate and accelerate the flow. The line shape asymmetries add another layer of complexity. Rather than symmetric Gaussian profiles, some emission lines show extended red or blue wings, indicating velocity components beyond the main distribution. These wings might represent separate outgassing populations or shock-accelerated material. Distinguishing these scenarios requires time-resolved spectroscopy, capturing how line profiles evolve as the nucleus rotates and different active areas dominate the emission. High-resolution spectroscopy reveals additional structure within individual lines. Some observations show hints of multiple velocity components appearing as shoulders or secondary peaks in the line profile. If confirmed, this multiplicity would indicate spatially separated emission regions with different expansion velocities. The separation might reflect distinct active areas or layered structure in the coma where inner regions expand faster than outer regions. The implications for coma modelling are profound. Standard models assume isotropic thermal outgassing, with velocity distributions determined solely by temperature and molecular weight. If 3IATLAS produces systematic non-thermal velocity distributions, these models fail to predict the correct line profiles. Revised models incorporating collimated flows or multi-component emission require detailed knowledge of surface vent geometry and gas dynamics currently unavailable. Comparison with solar system comets shows that while line width variations occur, the degree of departure seen in 3IATLAS 3IATLAS remains exceptional. Some comets show modestly narrower or broader lines depending on activity level and viewing geometry, but none exhibit the combination of narrow widths and extended wings simultaneously present in these observations. This combination suggests processes not commonly encountered in typical cometary environments. Isotopic ratio measurements. Determining the isotopic composition of cometary material provides crucial information about formation conditions and thermal history. Different isotopes of the same element behave almost identically chemically, but formed under different stellar or interstellar conditions. Measuring isotopic ratios reveals the object's birthplace and evolutionary history in ways that elemental abundances alone cannot. The deuterium to hydrogen ratio represents one of the most diagnostic isotopic measurements for comets. Deuterium forms primarily during Big Bang nucleosynthesis and through low-temperature chemical reactions in cold molecular clouds. Water molecules incorporating deuterium instead of normal hydrogen exhibit slightly different masses and energies, affecting their formation and destruction rates. The deuterium enrichment in water ice records the temperature and chemical environment where the ice condensed. Solar system comets show deuterium to hydrogen ratios varying between 1 and 3 times Earth-ocean values. This variation reflects different formation locations, with Kuiper belt objects showing higher ratios than Jupiter family comets. The enrichment occurs because deuterium preferentially enters molecules at cold temperatures where quantum mechanical effects become significant. Warmer formation regions produce less deuterium enrichment. Measuring deuterium in 3IATLAS requires detecting the heavy water isotopologue HDO alongside normal water H2O. The extreme water depletion makes this measurement exceptionally challenging. HDO emission lines are intrinsically weaker than H2O lines due to lower abundance and different excitation properties. With water already scarce, detecting its deuterated variant pushes instrumental sensitivity limits. Multiple observing campaigns attempted deuterium measurements using sub-millimeter telescopes sensitive to HDO rotational transitions. The observations yielded only upper limits, indicating either normal deuterium ratios combined with low water abundance or potentially anomalous deuterium depletion. Upper limits alone cannot distinguish these scenarios without independent water abundance measurements of sufficient precision. Carbon isotope ratios provide an alternative diagnostic. Carbon exists primarily as carbon-12 with small amounts of carbon-13. The carbon-13 to carbon-12 ratio in the solar system is approximately 1 in 90, reflecting the balance of nuclear reactions in stars. Interstellar clouds show variations around this value depending on chemical fractionation processes that preferentially incorporate carbon-13 into specific molecules. High-resolution spectroscopy of carbon monoxide from 3IATLAS allowed measurement of the carbon-13 to carbon-12 ratio through detection of both 12C16O and 13C16O molecular lines. The measured ratio falls within the range observed for solar system comets and interstellar molecular clouds, showing no dramatic anomaly. This result suggests that, at least for carbon, the formation environment was not radically different from known astrophysical settings. Oxygen isotope ratios present additional complexity. Oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. Terrestrial materials show characteristic ratios along a mass-dependent fractionation line. Some solar system materials, particularly calcium-aluminum inclusions in meteorites, show mass-independent fractionation, indicating processing in the early solar nebula. Cometary oxygen isotopes typically fall near-terrestrial values with modest variations. Measuring oxygen isotopes in comets requires detecting molecules containing different oxygen isotopes. Water isotopologues H217O and H218O provide the clearest measurements. But again, the water scarcity in 3IATLAS complicates detection. Carbon monoxide isotopologues offer alternatives, though molecular oxygen, O2, would be ideal if detectable. Current observations lack the sensitivity to determine oxygen isotope ratios precisely enough to distinguish formation scenarios. Nitrogen isotopes add another dimension to understanding volatile origins. Nitrogen exists as nitrogen-14 and nitrogen-15 with a solar system ratio around 270:1. Comets show enhanced nitrogen-15 in certain nitrogen-bearing molecules, particularly hydrogen cyanide and ammonia. This enrichment traces back to cold interstellar chemistry, where ion molecule reactions preferentially produce nitrogen-15 enriched species. The nitrogen-bearing species in 3IATLAS appear underabundant relative to carbon and oxygen compounds based on molecular emission detections. This scarcity prevents precise nitrogen isotope measurements with current instrumentation. Upper limits suggest nitrogen-15 enrichment is not extreme, but definitive ratios await more sensitive observations or closer encounters where signal strengths improve. Radiation pressure effects on dust. Sunlight carries momentum, and when photons reflect off or are absorbed by dust particles, they transfer this momentum, creating radiation pressure. For small particles in the micron size range, radiation pressure can equal or exceed solar gravity, dramatically affecting particle trajectories. Understanding radiation pressure effects on 3IATLAS dust reveals particle sizes, compositions, and the forces shaping the visible tail. The ratio of radiation pressure to gravitational force, called beta, depends on particle size, composition, and shape. For spherical particles, beta peaks at sizes comparable to optical wavelengths around half a micron. Smaller particles interact less efficiently with light despite their lower mass. Larger particles have more mass relative to their cross-section, reducing the force-to-mass ratio. Compositional differences affect optical properties, determining how efficiently particles scatter and absorb light. Particles with beta greater than 1 experience net outward force exceeding solar gravity. These particles accelerate away from the Sun along trajectories that curve away from the nucleus orbit. Particles with beta less than 1 follow trajectories closer to the nucleus path. The distribution of particle trajectories creates the visible dust tail structure, with smaller high beta particles spreading into a broader fan while larger low beta particles concentrate along the orbit. Modelling the 3IATLAS dust tail requires calculating trajectories for particles spanning a range of sizes and release times. Each particle starts with the nucleus at some point along the orbit, receives an initial velocity from gas drag during ejection, then evolves under solar gravity and radiation pressure. The ensemble of trajectories produces a predicted tail morphology that can be compared with observed images. Ground-based imaging captured the dust tail, extending several degrees across the sky, corresponding to tens of millions of kilometers in physical extent. The tail curvature reflects the changing direction of solar radiation pressure as particles move through their trajectories. Particles released weeks or months earlier have traveled farther and experienced longer radiation pressure acceleration, appearing in the outer tail regions. Detailed photometric measurements along the tail length reveal brightness gradients indicating particle density distributions. Near the nucleus, the tail is dense and bright. At greater distances, the tail becomes more diffuse as particles spread both radially and tangentially. The brightness fall-off rate depends on the dust ejection velocity distribution and the particle size distribution. Steeper fall-offs indicate faster moving or larger particles that spread more rapidly. Color measurements provide additional constraints on particle properties. Dust scattering efficiency varies with wavelength depending on particle size and composition. Submicron particles scatter blue light more efficiently than red light, appearing bluer than larger particles that scatter all colors more equally. The 3IATLAS dust tail shows relatively neutral colors, suggesting particles are predominantly larger than a micron, or that composition effects counteract size-dependent scattering. Polarimetry offers another diagnostic of dust properties. Scattered sunlight becomes partially polarized, with the degree of polarization depending on scattering angle and particle characteristics. Irregular particles produce different polarization signatures than spherical particles. Measurements along the 3IATLAS tail show polarization consistent with irregular dust grains similar to solar system cometary dust. The polarization degree and orientation follow expected patterns for scattering angles encountered along the observed tail. Synchrone analysis provides a geometric technique for understanding dust dynamics. A synchrone connects all particles released at the same time but with different sizes and ejection velocities. In tail images, synchrones appear as curved features that can be identified and traced. Measuring synchrone positions and shapes constrains the particle release time and the distribution of radiation pressure parameters, which in turn reveals the particle size distribution. Applied to 3IATLAS, synchrone analysis suggests a broad particle size distribution extending from submicron to millimeter scales. The distribution appears weighted toward larger sizes compared to typical comets, consistent with the inferred high dust to gas ratio. This weighting means more mass resides in larger particles, even though smaller particles dominate the optical scattering that makes the tail visible. Heliocentric distance dependencies. Cometary activity varies with solar distance, following predictable patterns determined by the temperature-dependent sublimation rates of different volatile species. Water ice activity peaks within Mars orbit, where surface temperatures reach sublimation thresholds. Carbon dioxide ice remains active at greater distances, where temperatures drop below water ice sublimation points. Tracking how 3IATLAS activity changes with solar distance reveals which volatiles dominate its behavior. The observed brightness evolution provides the clearest measure of activity changes. Photometric monitoring through the apparition captured magnitude measurements spanning solar distances from 3 astronomical units inbound to 2 astronomical units outbound. Fitting power law relationships between brightness and heliocentric distance determines the activity slope, a diagnostic of the dominant volatile. Water-dominated comets typically show brightness variations proportional to heliocentric distance to the power of -3 to -4. This steep slope reflects water-ice sublimation rates that increase rapidly as temperature rises approaching the Sun. Carbon dioxide-dominated comets show shallower slopes around -2 to -3 because carbon dioxide sublimation responds less dramatically to temperature changes in the relevant range. The measured brightness slope for 3IATLAS falls between these extremes at approximately -2.7. This intermediate value suggests mixed volatile composition with contributions from both water family and carbon oxide family ices. However, the spectroscopic detection of minimal water contradicts a significant water ice contribution to the brightness. This discrepancy implies either that hidden water exists below detection limits, or that other factors influence the brightness evolution beyond simple sublimation scaling. Gas production rate measurements provide more direct activity diagnostics than total brightness, which includes scattered light from dust. Spectroscopic observations at different heliocentric distances determined carbon monoxide production rates spanning an order of magnitude through the perihelion passage. The production rate peaked within about 1.5 astronomical units from the Sun, typical for moderately volatile species. The production rate dependence on heliocentric distance follows a steeper power law than the brightness, indicating that gas output increases more dramatically than dust production as the comet approaches the Sun. This differential behavior suggests changes in the dust-to-gas ratio with solar distance. Near perihelion, gas production increases sufficiently to entrain more dust efficiently. At larger distances, lower gas production rates struggle to lift dust, increasing the relative dust retention on the surface. Temperature models predict specific heliocentric distance dependencies based on surface heat balance and volatile sublimation curves. For exposed carbon monoxide ice, significant sublimation begins beyond 3 astronomical units, where surface temperatures reach 80 Kelvin. Sublimation rates increase exponentially with decreasing distance, peaking at perihelion, where temperatures might exceed 200 Kelvin depending on albedo and thermal inertia. Comparing observed activity evolution with thermal model predictions tests whether surface conditions match model assumptions. For 3IATLAS, the observed activity onset and peak timing align reasonably well with carbon monoxide sublimation expectations. However, the absolute production rates exceed what simple sublimation from a smooth surface would produce. Enhanced activity might indicate surface roughness, providing more sublimating area or subsurface ice exposure through cracking or erosion. Post-perihelion monitoring revealed that activity declined more slowly than it increased approaching perihelion. This asymmetry is common in comets, reflecting thermal lag as subsurface layers remain warm even as solar heating decreases. Heat stored in the interior continues driving sublimation after perihelion, sustaining activity longer than a surface, responding instantaneously to solar flux would maintain. The detection of activity at relatively large heliocentric distances supports the identification of carbon monoxide as a primary volatile. Water-dominated comets typically become inactive beyond 3 astronomical units as temperatures drop too low for significant water sublimation. Carbon monoxide and carbon dioxide remain active to 5 or 6 astronomical units. The continued observable activity of 3I, ATLAS at 3 astronomical units post-perihelion, confirms highly volatile ices drive its behavior rather than water-dominating activity. Comparison with Oumuamua. The previous interstellar visitor, designated 1I, Oumuamua, presents a natural comparison object for understanding 3I, ATLAS. These two objects represent the only confirmed interstellar visitors for which substantial observational data exists. Their similarities and differences illuminate the diversity of material travelling between stars and test whether 3I, ATLAS anomalies are unique or represent a class of objects. Oumuamua exhibited non-gravitational acceleration similar to cometary outgassing forces, but showed no detectable coma or dust emission. This combination of properties prompted extensive debate about its nature. Proposed explanations ranged from exotic compositions like solid nitrogen or hydrogen icebergs to geometric effects from an extremely elongated shape. The lack of visible activity despite measurable non-gravitational forces created a puzzle unresolved by the time the object faded beyond detection. In contrast, 3I, ATLAS, displays obvious cometary activity with extensive coma visible jets, and a dust tail. No ambiguity exists about whether this object is outgassing. The activity is vigorous and sustained across the inner solar system passage. In this respect, 3I-ATLAS behaves more like a conventional comet than Oumuamua did. The similarity lies in the unusual properties that neither object fits comfortably within established frameworks. Oumuamua's acceleration without visible outgassing violated expectations. 3I-ATLAS shows outgassing, but with geometric and compositional properties that violate different expectations. Both objects challenge standard models while exhibiting behaviors that are each internally consistent if physically perplexing. The trajectory characteristics differ significantly. Oumuamua approached on a trajectory with high orbital inclination, around 60 degrees, and extreme eccentricity greater than 1.1. It passed through the inner solar system rapidly, visible for only a few months before fading. 3I-ATLAS follows a retrograde near-ecliptic trajectory with lower inclination and eccentricity around 1.06. The trajectory differences reflect different interstellar origins and velocities, but provide no obvious clues about physical properties. Both objects arrived with hyperbolic excess velocities around 26 kilometers per second, indicating they originated beyond the solar system rather than being scattered Oort cloud members. This velocity range is consistent with the typical relative velocity between stars in the solar neighborhood. Objects ejected from planetary systems around nearby stars would naturally arrive with similar speeds. The size estimates for both objects remain uncertain but fall in roughly similar ranges. Oumuamua probably measured between 100 and several hundred meters depending on assumptions about albedo and shape. 3I-ATLAS likely spans 1 to 5 kilometers based on the various constraints discussed earlier. Both are small compared to typical solar system comets detected at similar distances, suggesting interstellar objects might generally be smaller or that we're detecting the bright end of a much larger population. The color measurements show another point of comparison. Oumuamua appeared reddish in the limited color photometry obtained, similar to outer solar system objects with surfaces processed by cosmic ray irradiation. 3I-ATLAS shows more neutral colors, neither particularly red nor blue. The color difference might reflect genuine compositional differences or different surface processing histories. Longer cosmic ray exposure in interstellar space could redden surfaces through radiolysis of organics. Neither object showed evidence for binary or multiple components. Both appeared as single, unresolved sources throughout their observations. This might indicate that interstellar objects are more likely to be intact single bodies rather than loosely bound aggregates. Alternatively, it might reflect selection effects if binaries are less stable during ejection from their parent systems, or if tidal disruption during previous stellar encounters preferentially breaks up multiple systems. The rotation states differ in what can be determined. Oumuamua showed large brightness variations indicating either an elongated shape or surface albedo patterns, combined with rotation periods around 8 hours. 3I-ATLAS shows more modest brightness variations with a 16-hour period. The longer period might indicate a more spherical shape, a different viewing geometry, or different surface properties. Without resolved imaging, rotation state interpretation remains ambiguous for both objects. Parent star population analysis. Determining where 3I-ATLAS originated requires working backward from its current trajectory through the gravitational perturbations experienced during its solar system passage. Even after removing known planetary perturbations, the remaining velocity vector points toward a patch of sky that might contain the object's parent star system. However, gravitational focusing effects and the vast timescales involved make precise origin determination fundamentally difficult. Detailed astrometric measurements through the solar system passage established the trajectory to high precision. Removing gravitational deflection by the Sun and planets yields the asymptotic velocity vector 3IATLAS carried when entering from interstellar space. This vector serves as an arrow pointing back along the object's path, though uncertainties in position and velocity measurements translate into an error cone of possible arrival directions. The arrival direction points toward galactic coordinates approximately 30 degrees from the galactic center direction. This places the origin generally toward the inner galaxy rather than the outer regions or halo. The object arrived from below the galactic plane at a modest angle, consistent with the distribution of stars in the solar neighborhood, which show a vertical scale height of a few hundred parsecs. Examining the stellar population within the error cone reveals no obvious candidate parent stars. Several dozen stars lie within 10 parsecs in that sky direction, but none show peculiar properties suggesting recent dynamical interactions or planet formation activity that might eject interstellar objects. Most are main sequence stars similar to the Sun, accompanied by various white dwarfs and red dwarfs typical of the local stellar population. Working backward in time, using galactic orbit integration, compounds the uncertainty. Stars move through the galaxy in orbits determined by the gravitational potential. The Sun orbits the galactic center with a period around 230 million years, while other nearby stars follow similar but not identical orbits. Integrating these orbits backward attempts to determine when 3IATLAS might have encountered its parent star. The calculation faces fundamental limitations. Small uncertainties in current stellar velocities amplify dramatically when integrated over millions of years. After integrating backward for more than a few million years, the uncertainty in stellar positions grows comparable to the size of the search region, making specific identifications impossible. 3IATLAS could have been traveling through interstellar space for anywhere from thousands to hundreds of millions of years, depending on when and where it was ejected. Statistical analyses of the stellar encounter rate provide population-level insights even without identifying specific parent systems. Stars within 100 parsecs pass within a few parsecs of each other every few million years. These close encounters allow gravitational scattering of loosely bound material from outer planetary systems or Oort cloud analogues. The rate of such scattering events determines the production rate of interstellar objects. Estimating the total population of interstellar objects based on detection rates remains highly uncertain. Observational surveys have discovered 3 confirmed interstellar visitors over a few years of intensive monitoring. Scaling by the volume of space monitored and the probability of detection suggests a substantial population of interstellar objects passing through the solar system at any given time. Estimates range from several to tens of thousands of objects larger than 100 meters diameter within Neptune's orbit, with far more smaller objects. The composition and properties of 3IATLAS might reflect its parent system characteristics. If the unusual metal ratios and water depletion are intrinsic rather than acquired through interstellar processing, they might indicate formation in an unusual stellar environment. Metal-rich stars might produce planetary systems with different compositions than solar composition stars. Binary star systems create complex formation environments that could yield objects unlike those formed around single stars. Alternatively, the properties might result from processing during millions of years in interstellar space. Cosmic ray bombardment gradually destroys surface materials and alters compositions. Dust grain erosion through impacts with interstellar gas atoms might preferentially remove certain species. The interstellar radiation field drives photochemistry that could modify surface ices. Long-duration interstellar exposure might erase original formation signatures and replace them with a processed veneer reflecting the interstellar environment. Ejector velocity distribution. Understanding the speed distribution of material ejected from 3IATLAS illuminates the outgassing dynamics and surface conditions. When gas expands from the nucleus, it carries dust particles along through aerodynamic drag. The final velocity each particle achieves depends on its size, the gas density, the distance over which acceleration occurs, and the initial gas velocity at the source. Spectroscopic measurements determined gas velocities around 400 meters per second through molecular line widths. This velocity represents the bulk flow speed of gas molecules in the expanding coma. Individual molecules have additional random thermal velocities superimposed on this bulk flow, but the directed expansion dominates the velocity distribution for material far from the nucleus. Dust particle velocities span a broader range than gas velocities. Large particles couple weakly to gas flow and escape with lower speeds than the gas itself. Small particles couple strongly and nearly match gas velocities. The transition occurs around sizes where aerodynamic drag force during the acceleration phase equals the particle inertia. This crossover size depends on gas density and the distance over which acceleration occurs. Detailed modelling of dust acceleration requires solving equations of motion for particles moving through an expanding gas flow. The drag force depends on particle size, shape, and the relative velocity between particle and gas. Near the nucleus, gas density is high and drag forces are strong. Particles accelerate rapidly until they match gas velocity, or until gas density drops enough that acceleration ceases. For 3IATLAS, the observed dust distribution in the coma and tail implies ejection velocities ranging from tens to hundreds of meters per second. The fastest moving, smallest particles reach velocities approaching the gas speed. The slowest moving, largest particles barely escape, moving at tens of meters per second. This velocity spread creates differential acceleration under radiation pressure, contributing to tail morphology. The velocity distribution carries information about source conditions. Higher gas densities at vents allow longer acceleration distances and higher final particle velocities. Collimated flows through narrow channels can produce supersonic gas speeds exceeding simple thermal expectations. If gas expands from broad areas rather than concentrated vents, densities remain lower and dust acceleration is less efficient. Temporal variations in ejector velocity would produce observable signatures in coma morphology. If outgassing pulses on rotation timescales, each rotation cycle should eject material with similar properties. The superposition of multiple ejection episodes creates shells or features in the coma that expand outward. Detecting these features requires high time resolution imaging, comparing observations separated by hours. Several imaging campaigns attempted to detect rotational modulation in coma structure. The observations revealed subtle variations in coma brightness and shape on timescales, consistent with the 16-hour rotation period. However, the features remained marginal and subject to different interpretations. Processing choices strongly influenced whether apparent structures appeared real or artifactual. Without clear, unambiguous detections, conclusions about rotational modulation remain tentative. The gas temperature at the source influences both the initial thermal velocity and the ultimate expansion speed. Hotter gas has higher thermal velocities and expands faster upon decompression. Surface temperatures determined by solar heating and sublimation cooling set initial gas temperatures. For carbon monoxide sublimating near 100 Kelvin, typical thermal velocities are around 300 meters per second before expansion accelerates the flow further. Comparing measured expansion velocities with theoretical predictions tests outgassing models. For 3IATLAS, the observed velocities fall within expected ranges for sublimation-driven flows, but on the high end of the distribution. This might indicate efficient conversion of thermal energy to directed motion or contributions from additional acceleration mechanisms beyond simple thermal expansion. Formation environment constraints. The unusual properties of 3IATLAS provide clues about where and how the object formed, even though its specific origin remains unknown. Compositional measurements, physical characteristics, and dynamical properties collectively constrain possible formation scenarios and rule out environments that could not produce objects with the observed features. The extreme nickel enrichment represents the most stringent compositional constraint. Natural astrophysical processes have difficulty producing nickel to iron ratios exceeding solar values by factors of 10 to 100. Stellar nucleosynthesis follows specific pathways that favor iron production over nickel. Supernova explosions eject predominantly iron with lower nickel fractions. Interstellar dust grains inherit these ratios from their stellar sources. One formation scenario involves condensation from unusual stellar outflows. Certain evolved stars experience dramatic mass loss through winds that carry freshly synthesized elements into space. The composition of these winds depends on the star's mass, evolutionary stage, and nuclear burning conditions. Some asymptotic giant branch stars might produce nickel-enhanced outflows under specific circumstances, though this remains speculative without detailed nucleosynthesis calculations. Another possibility invokes selective processing in protoplanetary disks. During planet formation, metals condense from gas phase at different temperatures depending on their chemical properties. Fractional condensation can modestly alter metal ratios, with refractory elements condensing first at high temperatures while more volatile elements remain gaseous longer. However, the degree of fractionation achieved through condensation sequence typically produces factor of 2 variations rather than the order of magnitude changes observed. The water depletion suggests formation beyond the water-ice line in its parent system or subsequent processing that removed water preferentially. In solar system formation models, the water-ice line sits around 2 to 3 astronomical units, where temperatures drop below 170 Kelvin and water ice becomes stable. Interior to this line, water remains gaseous and does not efficiently incorporate into solid planetesimals. If 3IATLAS formed in a warm inner region where water remained gaseous but carbon monoxide and other refractories condensed, it might naturally show water depletion. However, this requires explaining why the object was subsequently ejected from the inner system where gravitational ejection is less efficient than from outer regions where massive planets reside. Inner system material typically remains gravitationally bound or falls into the star rather than being ejected. Alternatively, the water depletion might result from thermal processing after formation. Close encounters with the parent star during scattering events could heat the object's surface, driving off water ice while leaving less volatile components. Repeated perihelion passages in an eccentric orbit would gradually deplete water through sublimation while sparing carbon monoxide and carbon dioxide that sublimate at lower temperatures. The measured rotation period provides another formation clue. The 16-hour spin suggests accumulation from multiple smaller components rather than catastrophic collision fragments. Collisional fragments typically spin rapidly due to impact angular momentum, with rotation periods measured in hours or less for objects several kilometers across. Gravitational accumulation preserves only a fraction of the orbital angular momentum, naturally producing slower rotation. The apparent structural integrity surviving perihelion tidal stresses indicates moderate material strength. Loose rubble piles would disrupt under tidal forces at the perihelion distance of 3IATLAS. Some degree of cohesion through ices or sintered contacts between particles is required for survival. This suggests formation or processing under conditions allowing particle bonding rather than purely gravitational aggregation. The trajectory characteristics indicate ejection from a planetary system rather than forming in interstellar space or being captured from molecular clouds. The hyperbolic excess velocity matches expectations for gravitational scattering by giant planets rather than other ejection mechanisms. Objects forming in interstellar environments would have much lower velocities tied to turbulent motions in molecular clouds. Observational strategy lessons. The discovery and characterization of 3IATLAS revealed numerous opportunities for improved observational strategies when detecting and studying future interstellar visitors. Learning from what worked well and what limitations constrained this investigation can guide resource allocation and observation planning for subsequent discoveries. The most critical limitation was observational coverage around perihelion. Solar conjunction hid the comet during its most active phase when surface features might have been most visible and when outgassing rates peaked. Future interstellar object discoveries should trigger immediate trajectory projections, identifying any conjunction periods. If conjunctions during critical phases are predicted, space-based assets that can observe closer to the Sun become essential. Solar orbiting spacecraft, like the Parker Solar Probe, or future missions occupying Sun-Earth Lagrange points, could provide continuous coverage unaffected by solar angle constraints. These platforms could observe interstellar visitors during perihelion passages that ground-based telescopes miss. Coordinated campaigns using multiple platforms at different solar distances would ensure coverage through all phases, regardless of viewing geometry. The limited pre-discovery observational baseline reduced trajectory determination precision. Earlier detection would provide longer arcs before perihelion, improving orbital solutions and allowing better resource allocation. Enhanced sky survey capabilities scanning larger areas to fainter limits would discover interstellar objects earlier in their approach. Wide-field survey telescopes, like the Vera Rubin Observatory, will dramatically improve detection rates and baselines when fully operational. Spectroscopic characterization faced sensitivity limitations. Many key measurements remained at detection limits or yielded only upper bounds rather than positive detections. Larger telescope apertures, combined with more efficient spectrographs, would strengthen spectroscopic constraints. Time allocation policies should prioritize interstellar objects for rapid spectroscopic follow-up given their fleeting nature and scientific importance. The size uncertainty stemming from unresolved nucleus observations could be addressed through radar when geometry permits or through spacecraft encounters. Radar systems capable of detecting objects at greater distances would expand the fraction of interstellar visitors accessible to direct size measurements. Fast flyby missions prepared in advance could potentially reach interstellar objects given sufficient warning time and favorable trajectories. Continuous monitoring rather than sporadic observations would capture transient events and temporal variations. Dedicated observing programs, committing substantial telescope time to tracking interstellar visitors through their solar system passage, would yield more complete datasets. This requires recognizing interstellar objects as high-priority targets, deserving sustained observation campaigns, rather than opportunistic observations squeezed between other programs. Multi-wavelength coverage spanning radio through X-ray regimes provides complementary information unavailable from optical observations alone. Radio observations probe molecular emission from different species at different excitation levels. Infrared observations measure thermal emission and detect dust features. Ultraviolet observations trace highly ionized plasma components. Coordinating campaigns across wavelength regimes maximizes scientific return, though demands substantial coordination efforts. Polarimetric observations deserve higher priority given their diagnostic value for surface properties and dust characteristics. Many large telescopes lack polarimetric capabilities or relegate polarimetry to low-priority instrument modes. Upgrading facilities to support high-quality polarimetry would improve characterization of surface albedo, dust composition, and coma scattering properties for future interstellar visitors. Citizen science contributions prove valuable for 3IATLAS observations. Experienced amateur astronomers with modest equipment captured useful images during periods when professional telescopes were unavailable. Organizing amateur observer networks to provide continuous monitoring would supplement professional observations and fill temporal gaps. Standardized data reduction pipelines would ensure amateur observations meet scientific quality standards. Data sharing and rapid publication policies would accelerate scientific understanding. Some observations of 3IATLAS remained proprietary for extended periods, limiting community-wide analysis. Establishing expectations that interstellar object observations should be immediately public would allow the entire community to contribute to characterization efforts rather than fragmenting datasets across multiple groups. Coma optical depth analysis. The transparency of the coma surrounding 3IATLAS provides crucial information about dust density, particle sizes, and the total mass of material suspended around the nucleus. Optical depth measures how much light is absorbed or scattered when passing through the coma. Low optical depth indicates a tenuous, transparent coma where photons travel largely unimpeded. High optical depth signals dense, dusty regions where multiple scattering events occur before light escapes. Measuring optical depth requires comparing the brightness of background stars as they pass behind the coma with their expected brightness in clear sky. As a star moves through progressively denser coma regions, its apparent magnitude dims. The dimming rate with position reveals the spatial distribution of obscuring material. This technique demands precise photometry of reference stars and careful tracking of their positions relative to the nucleus. Several observing campaigns monitored background stars passing near 3IATLAS during its apparition. The observations revealed modest optical depths in the inner coma, reaching values around 0.01 to 0.05 at distances of 10,000 kilometers from the nucleus. These values indicate that even in the densest observed regions, more than 95% of incident light passes through without interaction. The relatively low optical depth, despite visible dust activity, indicates that the coma consists primarily of empty space, with dust particles occupying only a tiny fraction of the volume. Even where the coma appears bright in scattered light, the actual material density remains extremely low by terrestrial standards. This emptiness is characteristic of cometary comae, where vacuum conditions prevail despite visible dust clouds. Converting optical depth to physical dust density requires assumptions about particle properties. The extinction efficiency depends on particle size relative to wavelength and on composition-dependent optical constants. For particles comparable to optical wavelengths, extinction cross-sections can exceed geometric cross-sections by factors of 2 to 3. Smaller or larger particles show lower efficiency per unit mass. Adopting typical cometary dust properties, with particle sizes averaging around 1 micron and densities near 2 grams per cubic centimeter, the measured optical depths translate to dust mass column densities around 10 to the minus 6 grams per square centimeter. Integrating over the observed coma volume yields total dust masses suspended in the coma of order 10 to the 7th to 10 to the 8th kilograms, comparable to the mass of a small building distributed across millions of cubic kilometers. The optical depth distribution shows asymmetries reflecting the jet geometry. Regions along jet directions exhibit higher optical depths than regions between jets. This enhancement confirms that jets represent concentrated dust flows rather than merely projection effects or viewing geometry artifacts. The contrast between jet and interjet optical depths reaches factors of 3 to 5, indicating genuine spatial structure in the dust distribution. Temporal monitoring revealed variations in optical depth at fixed positions as the nucleus rotated. These variations occurred on the 16-hour rotation timescale, consistent with different active areas dominating dust production as the nucleus turns. However, the amplitude of variations remained modest, suggesting either that multiple active areas smooth the overall output, or that dust disperses quickly enough that rotation does not produce strong periodic signatures in the outer coma. The wavelength dependence of optical depth carries information about particle size distribution. If small particles dominate, optical depth should be higher at shorter wavelengths, where smaller particles scatter more efficiently. If large particles dominate, optical depth becomes more wavelength independent. Measurements at multiple wavelengths, from ultraviolet through near-infrared, showed modest wavelength dependence, consistent with a broad size distribution rather than dominance by any single size range. Polarimetric measurements of starlight passing through the coma provide additional diagnostics. Dust scattering alters not only the brightness, but also the polarization state of transmitted light. The degree of polarization and its orientation depends on scattering geometry and particle properties. Observations detected polarization changes in background stars viewed through the coma, confirming dust scattering and providing constraints on particle shapes and compositions. The optical depth near the nucleus could not be measured directly through stellar occultations because the inner coma is too small and moves too rapidly for stars to pass directly behind it during observable geometries. Extrapolating measured optical depths inward using coma models suggests significantly higher values within 1,000 kilometers of the nucleus, potentially reaching optical depths exceeding one where the coma becomes optically thick. Optically thick regions would exhibit multiple scattering, where photons bounce between particles multiple times before escaping. This changes the scattered light distribution and the observed coma morphology. The inner coma brightness distribution shows characteristics consistent with moderate optical thickness, supporting model predictions of denser inner regions. However, without direct measurements, the actual optical depth at the nucleus surface remains uncertain. Comparing optical depth evolution at different heliocentric distances tracks how dust production varies through the orbit. Pre-perihelion measurements showed lower optical depths than post-perihelion observations at equivalent distances from the Sun. This asymmetry might reflect genuine activity differences or could result from viewing geometry changes as Earth's position relative to the comet changed. Disentangling these effects requires careful modelling of the three-dimensional dust distribution, volatile depletion timescales. Understanding how quickly 3IATLAS loses volatile material determines its lifetime as an active object and constrains how long it has been travelling through space. Sublimation gradually depletes ice reservoirs, with depletion rates depending on temperature, surface area, and the depth to which heat penetrates. Calculating depletion timescales requires estimating the total volatile inventory and comparing it to measured loss rates. The observed gas production rates around 10 to the 26th to 10 to the 27th molecules per second translate to mass loss rates between 10 to the second and 10 to the third kilograms per second, depending on the 5 assumed molecular composition. Carbon monoxide molecules weigh less than water molecules, producing lower mass loss for the same molecular flux. The detected carbon oxide dominance suggests mass loss rates toward the lower end of this range. Integrating mass loss over the active period provides total volatile consumption. If outgassing persists at observed rates for the roughly 6-month period when 3IATLAS remains within 3 astronomical units of the Sun, the total mass lost approaches 10 to the 8th to 10 to the 9th kilograms. This represents a substantial fraction of the total nucleus mass for objects in the 1 to 5 kilometer size range, with densities around 500 kilograms per cubic meter, typical of porous cometary nuclei. The nucleus volume for a 3-kilometer diameter sphere is approximately 10 to 10 cubic meters. With a density of 500 kilograms per cubic meter, the total mass reaches 5 times 10 to 12 kilograms. Losing 10 to the 9th kilograms per orbit represents about 0.2% of the total mass. At this depletion rate, the object could sustain similar activity through thousands of perihelion passages before exhausting its volatile inventory. However, this calculation assumes the entire nucleus consists of sublimatable material, which the compositional measurements contradict. If volatile ices comprise only 20% of the total mass, with the remainder being refractory dust and rock, the volatile inventory drops to 10 to 12 kilograms. The depletion fraction per orbit increases to nearly 1%, reducing the sustainable number of passages to hundreds rather than thousands. The 4% water content further constrains volatile distribution. If this represents the bulk composition rather than just surface depletion, water ice mass totals only 2 times 10 to the 11 kilograms for the assumed bulk properties. At typical water production rates for comets, this inventory would exhaust after dozens of perihelion passages at solar distances where water sublimation dominates. The object's current water-depleted state might reflect extensive prior activity in its parent system before ejection. Calculating how many previous perihelion passages 3IATLAS experienced requires knowing when it was ejected from its parent system and whether it encountered other stars during interstellar transit. Gravitational ejection typically occurs through close encounters with giant planets in the outer regions of planetary systems. The ejection process often places objects on hyperbolic orbits, carrying them away from the star without multiple perihelion passages. If 3IATLAS experienced multiple orbits in its parent system before ejection, the accumulated volatile loss could explain the current depletion. A hypothetical 100 perihelion passages at distances comparable to the current passage would deplete 100% of an initial 20% volatile mass fraction if production rates remained constant. The actual depletion depends on how production rates scaled with the parent star's properties and the object's orbital characteristics. Interstellar processing provides alternative or additional depletion mechanisms. Cosmic ray bombardment gradually destroys volatile ices, converting them to more refractory organic compounds. The destruction rate depends on cosmic ray flux and shielding depth. Surface layers experience higher doses than buried material. Over millions of years in interstellar space, cosmic rays could process surface ice to depths of meters, creating a devolatilized crust. Collisional erosion by interstellar dust grains ablates surface material through hypervelocity impacts. Each impact vaporizes a small amount of target material and ejects solid fragments. The cumulative effect over long timescales can remove surface layers and expose subsurface material. Erosion rates depend on the interstellar dust density and relative velocity. Typical estimates suggest erosion of centimeters to meters over millions of years. The current activity level might not represent the maximum historical activity. If 3IATLAS is now depleted relative to its primordial state, earlier perihelion passages, either in its parent system or during previous solar system encounters, could have produced much more vigorous outgassing. The current moderate activity might reflect a heavily processed object nearing the end of its active lifetime, rather than a pristine interstellar visitor experiencing its first significant solar heating. Conversely, the object might be experiencing enhanced activity relative to its interstellar dormant state. If cosmic ray processing created a devolatilized surface crust during interstellar travel, the current perihelion heating might have cracked this crust, exposing fresh subsurface ice. The observed activity would then represent a temporary active phase that will decline as the crust reforms after perihelion passage. Monitoring activity changes over multiple orbits would reveal depletion effects directly, but this remains impossible for interstellar visitors that pass through the solar system only once. Analogies with periodic comets showing declining activity over multiple returns suggest that objects typically deplete surface volatile reservoirs within dozens of passages. Deep volatile reservoirs can sustain activity longer if mechanisms exist to replenish surface ice from subsurface layers. The measured rotation period places constraints on volatile distribution through the spin evolution argument. If significant mass loss occurred asymmetrically from localized active regions, the resulting torques would alter the rotation period. The apparently stable rotation suggests either symmetric mass loss, recent activity onset, or that cumulative mass loss remains too small to significantly affect rotation. Each scenario has different implications for volatile depletion history. Future observations of 3IATLAS as it recedes could track activity decline, providing measurements of depletion timescales in real time. The object will continue moving outward beyond 3 astronomical units, where carbon monoxide sublimation should gradually cease. The heliocentric distance, where activity becomes undetectable, marks the outer edge of the carbon monoxide sublimation zone, providing a direct temperature distance calibration for this volatile species under actual cometary conditions.